Hello, class. This is an example video for Unit 5.3. In Unit 5.3, we are learning about distributable loads and also building upon the other things that we've learned in Units 5.1 and 5.2. And for this particular example video, I'm going to work through problem 5-155 from the 13th edition of the book, which looks like this. We have this L-shaped beam, and it has distributable load here on the side and one on the top. And so I've gone ahead and redrawn that here on the board of the dimensions and the forces and everything. And what we're being asked to find is the equivalent resultant force, and they want to specify where its line of action intersects in BC as measured from point C. So a distributable load, it's if you've taken physics class and learned about pressure, it's sort of the same idea, right? It's a force that's distributed along an area, or in this case a line. And so instead of having units of newtons, it's going to have units of or pounds, is going to have units of newtons per meter or pounds per foot, or that sort of a thing. And so to deal with them, basically you can always replace a distributed load with a single force acting at a certain point. So let's go ahead and get started and see how we would deal with this. So let's start by looking at this area here on the side. We want to find a force that represents. So this shape is rectangular. So really, we're just going to take the area of this box. So it has a length of 5 meters and a height of 200 newtons per meter. So if we just say the force of 1, basically we're going to replace all of this with a single force that looks like this. So force 1 is going to be going in the negative x direction. So minus 200 is the height, 200 newtons per meter, and then we got to times that by the distance it travels over, which is 5 meters. So at 200 newtons per meter times 5 meters leaves us with units of newtons. It's going to be minus 1,000 newtons, and that is in the negative z direction. So that's the magnitude. We also need to know, where does that force show up, right? We can't just place that anywhere. It's got to be, at the equivalent spot so that the forces and moments feel the same. So since the shape is rectangular, it's just going to be right in the middle, right? This is 5 meters, so it's going to be at 2.5. So since ultimately we're going to be trying to find the distance in terms of this line, I'm going to measure it from this line. So it's going to be minus 2.5 from line BC. So the distance one can be minus 2.5 in the y direction. Okay, so we're going to keep that in the back pocket. For this shape up here now, we're going to solve. We're going to split this into two separate shapes. So we have a rectangle and a triangle that's layered on top of it. So we'll end up with a force for the rectangle, which we'll call F2, and a force for the triangle we'll call F3. Those are both going to be in the positive y direction. So F2, just like with this area over here, it's rectangular. So it's going to be 100 newtons per meter times 6 meters, leaves us with I missed this. These arrows are going down. These arrows are going down. My bad. So, check the free body diagrams. Changed problem quite a bit. That's Sorry about that. I wasn't paying attention. So these forces are not acting up, they're acting down. So negative 100 times 6 equals negative 600 in the y direction. And F3, it is in a triangular shape. So the area of a triangle is 1/2 times the base times height. So the height is really it's only 100 because it's even though it's 200, it's just 200 minus 100, right? So it starts at 0, goes up to 100 from minus 1/2 times 100, also times 6. So that'll give us minus 300 in the y direction units of newtons. And distance 2, just like with distance 1, it's half of the span. And since we are going to be measuring from here, from point C, that is minus 3. In the x direction. And distance 3 is where this force acts. It's not going to be halfway because it's a triangle. It's going to be 2/3 of the way of that span. So it's going to be minus 4 in the x direction. Okay, so we're trying to find an equivalent force, just like in Unit 2, we're trying to find, for 5.2, we're trying to find equivalent force and figure out where we need to place it to cause the equivalent moment. So first, let's find our resultant force, which of course is just going to be F1 plus F2 plus F3, which is going to be minus 1,000 minus 900 newtons. And they may ask for you, to not give it in terms of Cartesian. Maybe they want it as a magnitude and an angle, in which case, right, we've been doing this since the start. So the resultant force magnitude is just the square root. So the sum of squares. Be 1,345.4 newtons. Acting at an angle as the angle, that would be the inverse tangent as the negative 900 over negative 1,000. But you got to be careful, right? Since they're both negative, it's going in the third quadrant. So if you just plug that into your calculator, it may tell you something like 41 or sorry 42 degrees, but you have to add 180 to that because it's going to be the negative sign would cancel the calculator. So really, that's going to be 221.99 degrees if you're measuring from the positive x. So that's the force, that's the resultant force, and we just got to figure out where to place it. And we're going to do kind of the similar thing. So first, let's find the resultant moment about point C. So the moment about point C, since we already have all the forces and directions are nice and perpendicular, we can just do our F times sort of a thing. So force 1. Right, if we're going from this line down to where the force acts and curl our fingers, you see our thumb points into the board, going to cause a negative moment. So it's going to be minus F1 times D1. And force 2 from point C, you go this way here. Because the force is going down, it's going to cause a positive twist. Same with F3, it's going to cause a positive twist. Say plus F2 Q times dt plus F3 times D3. And I end up getting a moment about point C is minus 2500 from that, plus 1800 from that, plus 1200 from that, which I wind up with a moment of 500 Newton meters in a counterclockwise direction. So positive means counterclockwise. Okay, so we got that now. And what they were told specifically is that we're going to place this force somewhere along this line BC. So to get this force, we know that the moment C has got to equal that force. And because this is an x distance we're looking for, only the y component of this force even matters. So resultant y component of the resultant force times some mystery distance in the x direction. So we have 500 is going to equal just the y component of this force matters. So that's negative 900. Or I guess just 900. Okay. I don't have to keep the negative because the signs will come from right-hand rule. So 900 times dx. And dx is going to be 0.556 meters from C. So if we place this force out here, we're going to get an equivalent system that will fill the same forces in the same moments. So that's all there is. That's Unit 5 in a nutshell, just replacing forces and or force systems with single forces and couples, or just single forces placed at the right spot. So that's really the crux of it. So hopefully that is helpful and clears things up for you that you maybe didn't understand as well from the other videos and lecture material available. And as always, if you have any questions, just let me know.